Open Google Maps on your phone right now. Zoom in on the land and you get crisp roads, buildings, and valleys. Now just pan over to the ocean. You still see highly detailed, rugged mountain ranges and massive trenches. The transition is so seamless that you'd naturally assume we have a complete, accurate map of the seafloor, exactly like the one that destroyed the OceanGate Titan submersible in 2023. We can drop a rover millions of miles across the solar system and perfectly chart the red dust of the Martian landscape. Yet, right here on Earth, those beautiful ocean ridges on your screen are actually a digital illusion, a complex picture built on guesswork. To figure out how those guesses are made, we have to look up. Since radar beams bounce harmlessly off water, satellites orbiting the Earth have to map the bottom of the ocean by staring exactly at the surface. They do this by bouncing signals down to the water to measure its exact height. And water, it turns out, does not sit perfectly flat. Massive underwater features, like towering seamounts, carry a tremendous amount of mass. That mass exerts a slight gravitational pull, drawing the surrounding water toward it and creating a tiny, persistent bulge right on the ocean's surface. Conversely, a deep ocean trench represents an absence of rock. With less mass to exert a gravitational pull, the water directly above it forms a slight depression. By carefully tracking these surface bulges and dips from space, geophysicists can run the math backward to sketch out where the largest mountains and trenches must be hiding below. But this gravitational footprint is blunt. It only reveals massive, sprawling geographic structures. Anything smaller, a steep canyon, a jagged valley, or a sunken ship, is completely invisible to this math. That means the global map you see on your phone is essentially a blurry macro sketch, leaving the real, treacherous terrain entirely hidden. To get actual precision, we had to rely on sound. Since sound travels incredibly well through water, ships began pinging the seafloor with single-beam sonar. They would drop a single pulse of noise and time how long the echo took to return, giving them exactly one depth measurement. It was like trying to map a massive, pitch-black room using a laser pointer. A ship could record a thin line of numbers directly beneath its hull, but everything to the left and right remained a total mystery. In 1948, a geologist named Marie Tharp took on the seemingly impossible task of making sense of the scattered data. Working from an office because women weren't allowed on research ships, she began painstakingly connecting these isolated data points by hand, connecting the dots between sonar tracks. Her careful guesswork revealed a massive, continuous underwater mountain chain running straight down the middle of the Atlantic. It proved that the ocean floor was constantly spreading apart, providing the smoking gun for the theory of tectonic plates. Interpolation works well for massive global discoveries, but assuming what lies between sparse data points carries a severe risk, as the world learned in 2014 when Malaysia Airlines Flight 370 vanished over the Indian Ocean. Search teams initially relied on those gravity-based satellite maps, which depicted a flat, smooth search zone. Instead, their deep-sea equipment crashed into a nightmare terrain of hidden underwater volcanoes and jagged rift valleys that the macro maps completely missed. Filling in the blanks with math is fine for an app, but when you actually need to navigate the deep, those assumed flatlands become fatal blind spots. Today, we bypass blind spots using multi-beam sonar. Instead of a single vertical ping, a modern vessel sweeps hundreds of beams outward in a massive fan, carving out detailed, kilometer-wide 3D models of the terrain in real time. Because running a massive ship is incredibly slow and expensive, scientists are now relying on autonomous underwater vehicles, programmable drones that drop into the cold dock to systematically scan the bottom without putting human lives at risk. These drones are feeding into the Seabed 2030 project, an aggressive global push to completely map the ocean floor by the end of the decade. Thanks to an unprecedented sharing of data between universities and private companies, they've managed to map about 28% of the seafloor so far. Getting to 100%, however, is a geopolitical headache. Several nations intentionally withhold their high-resolution sonar data because knowing exactly where underwater ridges and canyons lie is crucial for hiding nuclear submarines. In 1977, the priority of these scans shifted from geology to biology. While mapping a rift near the Galapagos, researchers discovered hydrothermal vents violently blasting superheated mineral water into the freezing dark. Surrounding these vents were entirely unknown ecosystems, teeming with giant tube worms and bacteria. These organisms survive entirely on chemical energy from the Earth's crust, proving for the first time that complex life does not require the sun. Mapping the deep sea has evolved into the active discovery of a living, breathing alien world hiding right beneath our feet.